So 4.1 is the chain rule. And so basically this is taking everything that we've already done, but doing it when there's like a function and a function. So this is essentially for like a composite function. And like how we handle that situation. So use the given substitution in the chain rule to find dy dx. So these first ones basically are giving us like y is the sine of 7 minus 5x, and then u is 7 minus 5x. So they're telling us what the inside part of the function is. So essentially what we have when we're doing a chain rule problem is we have dy du and a du dx, and we multiply them by each other, which if you think about it like dy du times du dx, the du's would cancel, so you're ultimately left with dy dx. When we actually get into solving them more, I don't really think about it that way, but that's kind of the easy way to start out thinking about them, so that's why they do it this way. So dy du, and that's because it's the derivative of this with respect to this function in the middle. So we take the derivative of this outside whole function, basically. And then ultimately what's happening is we're then taking the derivative of the inside function as well. And they get multiplied, but they do it this way, so it's like in steps. So the derivative of sine is cosine, so this would be the cosine of 7 minus 5x. So whenever we're doing a chain rule, it's always the derivative of the outside times the derivative of the inside. So then du dx is the derivative of what was in here, which obviously they've found for us over here, or they've written it out. So then the derivative of 7 minus 5x is just minus 5. And then we combine it all together to get our dy dx, or you can still write it as y prime, of course. So we would have negative 5 times the cosine of 7 minus 5x. And later on, obviously this is just the first problem, but we'll get to sometimes there's like functions and functions and functions. So there's like actually like a lot more happening. Or inside of this, you may have a product rule or whatever. So it kind of like, this is definitely where it gets more tricky because you have to pay attention to all these little things and make sure that you like take the derivative of the inside. Like any trig function that is not just an x inside is going to be a chain rule. Now, you don't always have to think about it that way, because if it's like x plus 7 inside, obviously the derivative of x plus 7 is just 1. So we don't really have to think about it as a chain rule, but we need to be like, okay, that would be a chain rule if x was squared or there was a number in front of x or whatever, like this one was. Or even if x is negative, because obviously then that's would be a negative 1 if you take the derivative. So another one of these ones, number 6, y is equal to 5 times the cotangent of 2 over x, and then u is 2 over x. So anytime I have a like function like this where there's like a 2 over x or anything like a fraction inside, especially if it's just over x or like, 2x squared or whatever like that. A lot of times what I try to do is rewrite it like we've been doing, where I would rewrite this part as like 2x to the negative 1, just because then you don't have to run a quotient rule on it. So dy du is the derivative of this whole piece. So this would be negative 5 times the derivative of cotangent is, well, minus cosecant squared, which is why I put the negative out there. So cosecant squared of 2 over x. And then over here, du dx, the derivative of this would be negative 2x to the negative 2. So then, obviously, when I go to write my answer, I'm going to want to put this back in the denominator so I don't have negative exponents. So my y prime, or dy dx, however you want to write it, would be negative 5 times negative 2, so obviously positive 10 over the x squared, and then times cosecant squared of 2 over x.
Could you go back? I looked down and looked back up. I was confused.
To where? To right here?
Yeah, thanks.
So basically, I'm taking all of this and I'm multiplying it by each other. So I did the -5 times the -2 to give me the +10 on top in front of the cosecant. And then I basically just moved this to the bottom to make that -2 over x squared that got multiplied by the stuff in front. I honestly think this method, the way these first few problems are, it's a nice intro for you to start seeing the inner function. But if you've done anything with composite functions, I think it's literally just easier to just do the chain rule in your head and not have it written separate like this. I think it gets more confusing, but some people like it this way, so. We'll do one more of these ones. So 8, y equals the secant of the tangent of x, and u is the tangent of x. So my outer function is secant, my inner function is tangent. So dy du. Sometimes people like to think about this instead as the secant of u, which is essentially what the chain rule is doing for us. But you just have to remember, if you're doing what we call u substitution, which we'll get into farther down the line, but anyways, then you just have to remember to plug that tangent back in anywhere there's a u if you choose to go that route to write it. If it's something like this, I don't usually replace it with u because I don't really need to, but when it gets to be something more complicated and long, a lot of times I will replace it so I'm not having to write this super lengthy thing every single time, because obviously that gets to be a pain. So anyways, so we have the derivative of, let's just say secant, is secant of x tangent of x in general. So that means that the derivative of this thing right here would be the secant of the tangent of x times the tangent of the tangent of x. Because the x, where we normally would have the x, is really tangent of x right now.
Oh, okay.
Because that's a function in a function. Which is why it might be easier to see it if we do replace it as u and do secant of u, tangent of u, and then we go back and replace u after. But it really just depends. But now I'm not done, because that's only the derivative of the first part. I haven't taken the derivative of the inside yet. So the derivative of the inside is du dx. The derivative of tangent is secant squared of x. So now I multiply these two things together. And so because they're trig functions, it doesn't really matter, but I ultimately end up with y prime is, I'm just going to stick this out front, secant squared of x times the secant of the tangent of x times the tangent of the tangent of x. This whole long thing would be your answer, just multiplying these things by each other. Questions on those so far? All right. Because they love the position, velocity, acceleration things, there's one of those in this section as well. An object moves along the x-axis so that its position at any time t greater than or equal to 0 is given by x of t is equal to s of t, so just our position function. Find the velocity of the object as a function of t. So 10, s equals t cosine of pi minus 4t. So the derivative of this, obviously they're not giving us u anymore. But if I need to think about it, this is my u that I was dealing with before, anything inside. Now, I also have a product rule right now. Because I have t, and then I have this whole piece right here. So when I take the derivative of the second part, I have a chain rule. So, v of t is equal to the derivative of the first, well, the derivative of t is just 1, so I don't even need to write that, and then I copy this piece down, so the cosine of pi minus 4t plus t times the derivative of this. So the derivative of cosine is what?
Negative sign.
Yep, so I'm going to actually go over here and I'm going to change this to a minus. And then I have the sine of everything that was in the parentheses, so pi minus 4t. Now I have to take the derivative of what's in the parentheses of sine. So what's the derivative of pi minus 4t?
Negative 4.
Yep, so negative 4. So then I just simplify it down. I would get the cosine of pi minus 4t and then plus 4t sine of pi minus 4t. I would say chain rules are where what you get to and you really have to start to like really think about your derivatives of like what's happening, and they're all the same but they're all different at the same time. So like it's like this next problem that we're going to do is very different than the first ones that we've done and how it's like laid out. So anyways, but that would be all you have to do on that one. Obviously, we're going to get to ones where they give you at a specific time t that we're plugging in, but it's not what we're doing right now on those ones. So the next several problems are, like, next huge chunk of problems are literally just finding the derivative using the chain rule. And I plan on working a ton of them because, like I said, they're just all different, and just like learning the process, it's really just repetition that's going to help with the chain rule. So 14, we've got y equals, in parentheses, the cosecant of x plus the cotangent of x, all raised to the negative 1. So since if I just had this stuff not raised to the negative 1, obviously I would just have, just take the derivative. I could write this as 1 over these things and use the quotient rule, but the chain rule is actually probably faster and easier. It just kind of takes a little bit of getting used to. So the derivative of the whole outside thing, I like to think about it as if I just had x raised to the negative 1, what would the derivative of that be?
Just like negative 1x, or just negative x to the negative 2.
Yeah. So instead of x, we have what's in the parentheses. So this is negative, parentheses, cosecant of x plus cotangent of x raised to the negative 2. So that's the derivative of the outside part. Now I take the derivative of the inside as my chain rule. Now, as we get farther along, there's possibly going to be things other than just an x in here, so we might have a chain rule and a chain rule. Right now we don't, so we don't have to worry about that, but just giving you a heads up. So now I can take the derivative of the inside. So the derivative of cosecant of x is minus cosecant times cotangent. So negative cosecant of x, cotangent of x, plus the derivative of cotangent is minus cosecant squared. So I guess I can change this to a minus cosecant squared of x. So basically, this stuff in this first parentheses is all getting moved to the bottom and squared. And then on top, I'm multiplying this negative through, which is just going to make everything positive. So I'm going to distribute this negative to here and here. And then I don't have to worry about it on this part over here. So on top, I have positive cosecant of x cotangent of x plus cosecant squared of x all over cosecant of x plus cotangent of x squared. Now, a lot of people are tempted to stop here, but we can simplify this farther, at least we should try by taking out a cosecant of x from both pieces on the top and seeing if it will allow anything to cancel. Sometimes it does, sometimes it doesn't. So if I take out a cosecant of x, then I'm left with cotangent of x plus cosecant of x over cosecant of x plus cotangent of x squared. Well, the thing in parentheses on top and the thing on parentheses on bottom both would cancel each other, but obviously the one on the bottom is squared. So I'm going to get rid of the squared on the bottom, cancel out that cosecant plus cotangent on top. So my final answer then would be cosecant of x over cosecant of x plus cotangent of x would be my derivative of that. Don't like these as much as the other ones.
Especially if there's going to be chain rules inside of chain rules.
Yeah.
I just have to get the hang of it.
Yeah. It really is just like a repetition thing. Like once you do it a lot, it kind of just like second nature. You're just like, okay. But yeah, it does take a little bit. And I still sometimes like forget. I'm like, oh man, like especially when there's like chain rules and chain rules, I'll like take the outer one. That was like Virginia's biggest problem last year. She would like take one of them and forget to do the second one. I was like, Virginia, there's another one. But I do it too. I mean, it was just funny because she would do it and then Josh would look at her and be like, like, there's one more. 16. This one should be a little easier. Y equals x cubed times 2x minus 5 raised to the 4th. So if you really got in a bind on the AP exam and you forgot the chain rule, or you're like, I really don't think I did this right, whatever, you could obviously multiply this one out. It's just going to be really big, and then you can simplify it. And then you could simplify it. But that's going to take a long time to multiply all of that out. So chain rule, product rule, going to be nice here. So I have a product rule. So I have these two pieces. On this piece, I have chain rule.
Okay.
So the derivative of the first piece would be 3x squared. Then I have this chain rule part here. So it's the derivative of the outside. So I kind of like almost ignore everything that's written inside of it. And I'm like, okay, I'm just taking the derivative of a parentheses and just, whatever. So this would be times 4, and then everything inside the parentheses, so 2x minus 5, and then take 1 away from the exponent of the parentheses, so that's cubed. Now I take the derivative of the inside of the parentheses to finish off the chain rule of this piece. Oh, shoot. You know what I did?
Isn't it just the same thing first? Or are we doing the quotient rule first?
Product rule?
Yeah, or that's what I meant, yeah.
Yeah, so I shouldn't have even written this yet.
Yeah.
Okay.
I just thought that.
Backtrack. Copy this down. See, even I do it. Plus x cubed. Now I can rewrite what I was writing before. Times 4 times everything in the parentheses cubed. Now I need to take the derivative of the inside of my parentheses. So 2x minus 5, derivative of that would just be 2. And then now I can simplify it all. So I'm telling you, all the stuff like combined together really throws you for a loop sometimes. So simplifying it, I've got 3x squared times 2x minus 5 raised to the 4th. And then over here, combining everything on this side, I've got 8x cubed times 2x minus 5 cubed. Now, obviously, like I said earlier, like we could multiply all this through even here at the end and do that, but 99 times out of 100, they're leaving their answer right here. Because if you do anything else, it's just going to get more complicated. You could possibly consider taking out a 2x minus 5 cubed from both pieces, or well, and I guess an x squared, but you don't really need to do that. Like, I'm pretty sure if you look in the book, I'm pretty sure they just leave their answer like this. Is 16 like the one that they don't have it? Oh. They will leave it here, or they'll go one step farther to factor the stuff out, but I trust that you can factor, so if the answers were multiple choice and you had a factoring option, you'd be able to do that. $18. Y equals 4 times the square root of the secant of x plus the tangent of x. So any idea what I would have to do with this one to start with?
Square it. Get rid of
Well, then I would end up with y squared, and then that's going to get into something that we're doing no, not tomorrow. Whenever we get to 4.2. How else can I rewrite a square root? Like, what's another way I can rewrite a square root that means the same thing?
It's like the 1/2.
Yeah. Yep. So I would rewrite it this way first and foremost. So 4 times the secant of x plus the tangent of x to the 1/2. Because we can't really take the derivative of a square root per se. We can, because we can obviously write it as an exponent, but it has to be rewritten for us to do it. All right, so now we take the derivative of the outside. So 1/2 times 4 and all of that. So we've got 2 times everything in parentheses, so secant of x plus tangent of x, raised to the negative 1/2. And then all times everything inside, well, the derivative of everything inside. So the derivative of secant of x is secant of x tangent of x plus the derivative of tangent is secant squared of x So for the moment, I need to move this secant of x plus tangent of x to the negative 1/2. I need to move that to the bottom, and I'm going to go ahead and rewrite it as a square root. Sometimes in the answers, they'll leave it as a square root, and sometimes they'll change it back to a square root. Sometimes they leave it. Either way, it doesn't really matter. And then on top, because I see that both of these have a secant in them, I'm going to go ahead and factor it out so I can just save a step of having to write everything. So I'm going to have on top 2 secant of x, and then in parentheses, tangent of x plus secant of x over secant of x plus tangent of x to the 1/2. Now, a lot of times I leave this right here. However, this is the same thing as this. Would you agree that this is raised to the positive 1? So I could technically, instead of having moved this down here, I could have actually written this as 2 secant of x times the square root, or I could write it as, in parentheses, tangent of x plus secant of x to the 1/2 on top. Because these are the same, I can subtract their exponents, and then I would end up with it this way. or again, you could write it as a square root. So either of these would be fine. Just two different ways you could see it written to give you the same answer, basically. Which way does the book write this one? Number 18. The book goes to here, and then they write it as like a radical instead. But like I said, either way is really okay. If you stopped here, I would take the answer for you, like for a test or a quiz. More showing you this because, again, if they multiple choice question, sometimes they give it to you one way, sometimes they give it to you another way. Oh, that's a good question. All right, I'm going to do an odd one because it's one of those where it's a chain rule and a chain rule. So 23. It's not a hard one, fortunately. It's just a lot happening. Y equals 1 plus cosine squared of 7x all cubed. So just a notation thing. I know we talked about this last year, but the cosine squared of 7x is the same as the cosine of 7x all squared. I like this notation, the way I just rewrote this, better for doing chain rules. I think it's easier to see, and to where I don't forget like to do things. But again, up to you if you need to see it visually that way or not. So we're taking the derivative of the entire outside thing. So that's going to be 3 times everything in parentheses as it is. So 1 plus cosine squared of 7x. And then we raise that to the 2, because obviously we take 1 away. Times, well, the derivative of the inside, the 1 goes away, right, because the derivative of 1 is 0. And then I've got to take the derivative of this part. So, looking at it here, the derivative of the inside would be 2 times all of this. Then I have to take the derivative ultimately of this 7x that's inside. Oh, wait. I did not take the derivative. Derivative of cosine is not cosine. Derivative of cosine is, or wait, no. Hold on. Like I said, confusing. I had it written right the first time. I did the derivative of the whole outside thing. Now I do the derivative of inside. So I technically have a quadruple chain rule in this problem. Because of this being not just an x in here. Because I did the chain rule of this whole piece outside. But then I'm doing this piece. Then I'm taking the derivative of this and this. So, the derivative of the cosine of 7x then is minus 7x, or minus the sine of 7x. Get my words together here. So that's the derivative of the inside of this parentheses over here. So this is producing all of this. Then the derivative of the inside of this is 7. Or, well, with the negative sign over, well, wait, no. Positive 7, not negative 7, positive 7. So times 7. Are you tracking? Because I know this is a lot.
I think I just figured it out.
Okay. So then now I just need to simplify it all. So then I've got 7 times 2 times 3, so that's 42. I've got a negative on this sign over here, though, so I'm going to put the negative 42 out front. And then basically everything else is just getting multiplied So 1 plus the cosine squared of 7x all squared times the cosine of 7x times the sine of 7x. Too many sets of parentheses to deal with in this problem. Anyways, that's how you do that one.
I actually do think I'm gonna like these.
It's fun because do you like Sudoku puzzles?
Yeah.
It's like that.
I think I just figured it out after seeing all of that. I was confused at first, then I just went back and I kind of figured it out.
Yeah. They get to be a lot more fun once you have started to see it and you get it. It's like, oh, I enjoy doing this, but until it clicks with you, it's like I have no idea what I'm doing. It's like, okay, just follow the process. Yeah, I like them. It's just when it gets to be literally this one was 4, it gets to be a lot. So 24, y is equal to the square root of the tangent of 5x. So this one is, obviously, we've got multiple things happening here. Again, not as many as the last one, but still a couple. So I'd rewrite this one first. So the tangent of 5x all to the 1/2. So I'll see if you can tell me how to do this one this time.
The 1/2 times tangent of 5x. And then times
All that's raised to the what?
to the negative 1/2.
Yep.
And then times is this 2 and 1? Or
Yeah, there's going to be 2 because we need the derivative of tangent and then you'll need the derivative of the inside of it.
And then it'd be times secant squared of 5x. And then it would be times 5.
Yep. And then just simplify it after that, obviously. So we have 5 secant squared of 5x over 2, and again, I'm going to write it as square root this time because why not? Tangent of 5x. But yeah, seems like it seems like you've got it. We'll wrap up with one more for today. Because this will kind of end this little chunk of where we are right now. And I'll give you a few that you can try if you want to try them this weekend. If you want to wait and do them all when we finish the section, that's fine too. But just whatever. So 26, so we've got r is equal to the secant of 2 theta times the tangent of 2 theta. So theta is just x in our situation. If you don't like theta and you want to rewrite it as x, totally fine, obviously. So derivative of r. So we have product rule and chain rule. So I've got the derivative of this first piece, which is secant of x, tangent of x. So I've got secant of 2 theta, tangent of 2 theta. But this is a chain rule in this piece. So times the derivative of 2 theta is just 2. So I'm going to stick that 2 out front. and then times the second piece just as it is, so the tangent of 2 theta, plus the first piece as it is, so secant of 2 theta, times derivative of tangent of 2 theta would be secant squared of 2 theta, and then the derivative of the inside would just be 2, so I'm going to put a 2 out front again. So then at this piece, or at this point, again, just a matter of how you simplify it, but I would see at least 2 secant of 2 theta tangent squared of 2 theta plus 2 secant cubed of 2 theta. If you want to factor a 2 secant of 2 theta out, you can. But I don't think that's really going to do anything for me. Do they leave it here or do they keep going? What number is this? 26. Yeah, they just leave it here. So, but if you factored it out, not the end of the world. So, all right, so a few problems up to where we are now. 1, 9, 19, 25, and 27. Obviously, if you want to choose a few more, by all means, go for it. Oh, I didn't even realize they changed the instructions here to find dr d theta, because obviously the previous ones were find dy dx, but
Yeah.
we did it right. And then we'll get into, on Monday, a few second derivative questions with this stuff, like, because sometimes the first derivative isn't going to be a chain rule, but by the time you take the second derivative, then you're into a chain rule. So the first, yeah.
I'm gonna like this a lot.
And then we'll get into finding like the value of the derivative of the composite function at a point. So like once you get to this, they tell you what x is equal to, then we're solving it. And then finding the equation of the line tangent to the curve will also be part of this section of stuff. So, yeah, it is fun, but that's a good stopping point because, I mean, it seems like you are getting it. But if we don't get it up to this point, the rest of it's going to be a little challenging.